Greetings. Today's lecture will be about the short channel effect. So short channel effect means, sorry for the last or previous time, we wrote about the MOSFET and MOSFET for the long channel models. At the long channel models, there were many obstacles that can disturb our ideal case of the MOSFET operations, such as punch-through, or hot carrier effect, MOSFET breakdown, or some programs that happen but strong electric field. Anyway, they was ignored in the long channel. For short channel, let's see. For the short channel, the channel means some resistance. Okay, so the long channel, it was very long channel, so it means somewhat big resistance. So nearby contacted resistance will be smaller. So it was very ignored. But as a short, it became with the short channel, with the respect of short channel, as the channel size has been down, we can see the other resistance, plastic or contact issues anyway. So now we must consider some contact issues, since the contact or any plastic issues resistance has been come up to our respect and sight, and the size is not ignorable. Anyway, so what is short channel? For the long channel, it was very ideal case and some disturbance was ignored. But in the short channel, so why we use short channel? Several mobile device. This is my iPhone 7. So at this device, there are at least 100 million transistors inside in a CPU. So it means, let's guess, if one transistor was 1 centimeter space, then maybe for 1 million, maybe the room here I'm recording will be full of the transistors. But if it came with nanomillimeter size, that only few space, maybe some centimeter or 1 meter space will be used. So it means if the transistor and channel is getting smaller and smaller, in short to modulate, the efficiency of space saving and positing and saving the transistors more efficiently will be able. So it means the device that we use with the transistor, the size will be more smaller. Okay, so this is why we use a short channel. And now for now, we are looking for the 3 nanometer generation development. For now, it is 5 nanometer generation. So most biggest and common example of the 5 nanometers device or product will be the Apple's MacBook Pro, the M1 silicon chip. Anyway, so let's see. As we come with the short channel, there are many disturbance and problems. For first, punch through. Punch through means, okay, let's draw normal and fat. For the long channel, maybe at the pinch of state, since the channel was very long, the differential region has invaded the channel, but it doesn't matter, since the channel is very long enough to ignore. But with the short channel respect, let's guess, if the total channel length was 10 nanometer, that's for the case, and the invasion of the depletion was short, was 3 nanometer, and the effective channel length was 7 nanometer. Then the only working channel length will be about 7 nanometers, which can be compared by the 10 by 3. So very ineffective. And by this, we can say we can guess there is a problem for the short channel. Okay, so first, punch through. As I said previously, as the depletion has, let's guess, the source and drain. Let's guess. We just induce the voltage in the drain. Then, since the drain is N-type heavy top silicon, there will be some depletion enlarging. Okay. The channel modulation will be happened. Okay, and then the depletion will be more larger and larger, and finally overlapped. So the overlapped depletion layer will be another path of the electrons or carriers move away. So even at the off state, if we keep giving the voltage bias at the drain and source, it means from the source to drain, the electron will be attracted to the positive voltage and it will make the current flow, the IDS. So it will make the current flow in the off state. It means maybe it can be meant as the sub-threshold swing is bad, and it will make the power dissipation bad. Okay, so it means if for a mobile device like the cell phone or notebook, if this happens, maybe the battery's runtime will be more scaled, runtime will be more down, and maybe we can use it as a ideal case MOSFET or transistors. And secondary, threshold voltage is rolling up, which means the threshold voltage is down. So let's see. So there was a device that I just made. The threshold voltage was 5 volt for the gate voltage. And let's guess. If I induce the 5 voltage, then at the 5 over the 5 voltage or over it, the channel will be turned on state and the current will flow if the drain and source voltage is induced. But with the short channels, just the aspect of the half side, okay, source, oxide, and drain. So let's guess. As a short channel it came, if we have the big bias, the voltage in the drain part, then as we know, at the plus voltage, the energy band diagram will be down. So as it down, the horizontal electric field will affect to the oxide energy band diagram. So also here the right side of the oxide diagram state will be down. It means the threshold voltage is somewhat down, and totally the threshold voltage has been down and changed. So this is what I unwanted state. So for this case, it can be said as the drain induced barrier lowering. the barrier may be meant as the threshold voltage. Secondary jitter. Gate induced drain leakage. So, as a drain leakage means, let's see. So for the gate induced drain routing, if we keep the voltage in the drain side, then the depletion will be more enlarged, and as I let the voltage of the gate as offstate or low voltage, VGO, or under the threshold voltage, it means offstate. For the ideal case, current must not flow like this. Current must not flow, but in the jitter, we can see as the invasion of the depletion region in the drain side, the carriers can be moved from the depletion region from the sub to drain. Why it happens? So let's see. For the PN junctions, for the simple case, we know the center will be made of the depletion region, in short, depth region. So in the regions, there will be induced the strong electric field by the voltage induced. So by the strong electric field, carriers will be moved with the electric field. So we call this as a drift effect, and by this, the drift current will be happened. So this is the jitter. Okay, and some velocity issues. So I will erase the part that I just stopped. So, velocity issue for first, velocity saturation, and second, velocity degradation or downside, or speed of the down. So, let's see why velocity saturation happens. Okay, so for the drift, we know the both pairs use the drift velocity and the drift effect as the electric field for carriers to move. So, with the respect of the drift velocity, we can state the equation like this. If the electric field of the commission or singularity means the critical point of the electric field, so maybe the maximum electric field that it can have. So, if we get more strong voltage at the device, then the more strong electric field will be induced. So, if the electric field is over the critical electric field, then we, as the equations, if a electric field that is induced is more bigger than the critical electric field, then this will be more larger than the number 1. So, and maybe the numbers of the carriers is vary a lot. So, if it was under the 1, maybe we'll come to the nearby or diverse, maybe will be the 0, or if it is over the 1, then it will diverge to the real numbers, that is over 1. So, if the electron is over the critical electric field state, then the drift velocity will be more down. Or another case, if the electron is under the critical electric field state, then we call this as a low field mobility. Oh, here is the equation, sorry. So at this state, the mobility will be like this equation, and the drift velocity will be situation within the critical electric field state. So maybe at this case there will be used like this: the photon scattering, lattice scattering, maybe just for the big case there was two more, but I just forgot. Sorry. So anyway, if the carrier is faster, carrier is super fast, or have very fast mobility, as the carrier move, it will hit with another carrier, or some lattice, or molecules, and make the carrier pair generation. So if it keep happens, then we call this effect as the avalanche for the p-n junctions. Or in the MOSFET, we call, if this effect keep happens, then the carriers that have higher energy will be continue to be generated. So carriers, as the hot carriers increase by 2 times, 4 times, 8 times, and a lot of times, it will make the breakdown of the MOSFET that can't work as it was designed. So the hot carrier effect finally make the MOSFET breakdown. Or even, let's see if there was oxide. As the hot carriers keep hitting the oxide barrier, and after some time, the oxide layer will be damaged and maybe have some trap charge inside, or make a hole. Like this. So the carriers will move to the gate, is attracted to the voltage of the gate, and some others will move to the drain silicons as we designed. So it means the drain current we wanted to as the output is not ideal or lowered. So we call this as a MOSFET breakdown, and we can't use the device as we wanted. We designed. Hey, so we have solution around this. First, as the silicon insulations. Very simple. For the quantitative case, the depletion will be enlarged and finally overlapped. So to plot this, plot the source that happens as a depletion region. Insulator on the body. The depletion will not be enlarged as it happens, but it will have the downside scale of the current. I mean, so simply, for the previous case, we use the total cell body, and in this case, we use only this part. So, less carrier and less as the in this, the carrier number will be more down, and the current will be down. Okay. Or UTB SOI is same as SOI, but ultra dim body. Okay, for the small case, and body doping. So body doping was also derived from the solution of the punch through. Okay, so let's guess. at this case, as there is more carriers in the same space as the anti-habit of silicon is, so depletion layer will be like this. Tick, 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 tick. The depletion region of the P silicon side is more larger. So, if we have same or more heavy doped P-type substrate, then maybe from the previous case, the depletion ratio will be down. It's good, but it also have a problem. The velocity saturation as the heavy doping, scattering will be more easier to happen, and the velocity saturation will be happened. Okay, so LDD, light doped drain. So the drain silicon we write doped here, and then it means it's a gitter or punch through. The depletion region will be more down, as I said previously for the PN junction case. And third, pocket or hollow implant. Make some implant here to stop the enlarging of the depletion region that came from the reverse bias of the drain or source. Okay, and this is very important. The next generation MOSFET, FinFET and G88 gate all around. For the FinFET, see, the gate is covering the fin substrate, and the channel will be in just like this. So the depletion happens, the depletion effect will be downside, and maybe we can make the more effective and enlarged current flow and gate all around. Just think, this is the gate, and plus source drain here, maybe some air, and see, the gate is covering the nanowire or the wired body. That it means the channel will be induced through these nanowires, so the current can flow easily. Maybe the depletion region will be very smaller. Okay. And let's see about the sorry, I just forgot about talking the storage device. Storage device. With the theme, we can make some storage device like, for typical case, ROM, read only memory. Not now, not only in the memory, we can edit the date that ROM have inside, and RAM. So ROM for the development is a big case. Programmable ROM, erasure of a programmable ROM, enhanced EEPROM, and flash memory. For the RAM, so random access memory, which means the random access memory is the part of the main memory or ROM. RAM, that may be the medium sector of the saving the data that the CPU wants to use. The processor unit. Okay, so for the saving the data, let's see, here is the electrons. If I have the voltage wanted, then for 3 voltage, so third example, then the 3 is the amount of the 3 voltage, the electrons will came here as the oxide through the oxide. Why happens? As the oxide As the voltage is the outside form will be changed toward thinner, and maybe the electrons will be able to pass through this oxide. So this is how we save the data. And formula saved from this state, we need more high voltage. So, for erasing the data from these medium sectors, just induce the reverse voltage. Then, its amount of free voltage of the electrons will be get out. So this is how we erase the data. Okay, so here is the effect. As we storage more data in the cell phone more and more, then we can see the consumption of battery will be more faster and runtime will be down. This is why it happens. Okay, for now, single, multi, and triple. Okay, so there are 3 levels of a single, and multi, and 3. Okay, so for the 2-bit data, and 4 case of the data saving. And so it means 1 threshold voltage, 3 threshold voltage, and 7 threshold voltage here. So maybe it can be used as the ROM or the USB we use. Okay, thanks for listening. And maybe next time we will see another topic that maybe we never learned. Thank you.